Howdy everyone, Nir Regev here with another episode of Paper Talk, coming from this time Lake Tahoe again, and today we're going to cover a paper from the lab of Professor Gerbers in the University of Alabama that is titled Self-Supervised Contrastive Learning for Radar-Based Human Activity Recognition. Okay, let's carry on. What they do here, they propose a technique for augmenting RF-micro-Dopler data. How they're doing that? They're basically, when you generate these kind of spectrograms or images for the micro-Dopler signature, you use what we call a short-time Fourier transform, which is given by this. It's a representation of frequency and time, or frequency versus time, if you will, of a time domain signal. How does it do that? Calculating this integral, or absolute value of the squared of this integral. And this integral in applicable manner is calculated by FFTs. Okay? So we take a window or a part of the signal, we calculate the FFT and we put it as a row, and then we progress to the next part of the signal with some overlap, and we again compute the FFT, take the absolute squared, put it as another row, and that way we are forming a matrix. So they are proposing to augment the data by generating multiple representation of the same time domain signal by varying the window length that we're looking at and varying the amount of overlap that we're using. And lastly, varying the windowing function that we multiply by before we are calculating FFTs. Okay, here is another Kaiser window function that they give here instead of just the Hanning. Okay, so that way they are generating multiple resolution in time and frequency, as well as multiple side lobe and main lobe level attenuation by using a different window or window function. Okay, so they get a lot of images for the same time domain signal, and that is how they do the augmentation. Now, in terms of how they train the network, instead of using their well-known convolutional autoencoder network, self-train, they're using a branch here of physical aware GAN that is encoding its generated image through a latent representation, an MLP layer, multiple layer perceptron layer, and is generating the output, and this output is going to be in contrast to this output, so to speak, in terms of maximizing the agreement between those two. So this branch can basically learn to classify these images, at least as a way of initializing this encoder weights to generate the latent representation. This is the function in terms of contrastive loss, that's how they call it. And they conclude that this method is surpassing the convolutional autoencoder method by 4%. This is a very interesting paper. They go into how they do the self-supervised framework. They use a resnet here to generate representations. The encoder that they use is basically a resnet architecture, and they summarize the accuracy here in this table, table 1, and they conclude the paper. Now, this concept of physical or physics-aware GAN is something that they've done or published papers on the past. Here are the papers. I think 15 is their paper, maybe 28 and 30 as well. And it's very interesting, and that will be a topic for the next paper talk discussion. Thank you for listening. If you like my content, subscribe and like, and don't forget to follow me on LinkedIn and Twitter.